Two devices, same account, no internet, both updates the same data. Who wins? Welcome to the hardest problem in mobile system design, which is data synchronization and conflict resolutions. Let's talk about offline first architecture. Offline first means the local database is the source of truth. Network becomes sync mechanism, not primary dependency. The flow, user updates data and save it locally immediately. UI updates instantly. Sync runs in a background and the server responds. Resolve conflicts if needed. Why offline first matters, especially in emerging markets, point of sale systems, delivery apps, rural connectivity. The benefits: fast user experience, resilient, no blocking UI, better battery usage. Eventual consistency. In distributed systems, you cannot guarantee instant consistency everywhere. Instead, system becomes consistent eventually. This is common in microservices, multi-device apps, cloud sync systems, and used heavily by Amazon and Netflix. Comparison between strong vs eventual consistency. Immediate sync over time. Here slower, here faster. Complex, scalable. Banking core system and social feeds. Conflict scenarios. Scenario 1, multi-device update. If a user edits profile, device A change name to Omar and device B changes the name from Omar to Omar Ale. Both are offline. Now both think. Conflict. Scenario 2, point of sale terminal. Two terminals sell same item at same time offline. Stock 1 and both sell. Now stock equal -1. That's dangerous. Conflict resolution strategies. Last write wins. Latest timestamp overwrites the older one. The pros from that: simple and cons: data loss possible. It is good for profile fields, non-critical metadata. Conflict resolution strategies. Server authority. Server validates and decides. The pros: controlled logic, safer for financial apps, and the cons: more back-end complexity. It is good for payments, inventory, transactions. Versioning strategy. Each object has ID and version. If client sends outdated version, reject the update and forces client to refetch and merge. Conflict resolution strategies. Merge strategy. Combine changes intelligently. For example, if a user A edits email and user B edits the phone, no conflict, merge both. It is used in collaborative apps, document editors. CRDT, conflict-free replicated data types. Advanced distributed solution, data structure that automatically merge without conflict. Even if device is offline, updates concurrent, order different, it still converges to same state. Example for CRDT types: G counter, increment only, LWW, register, or set, observed, remove set. It is used in real-time collaborative applications and distributed databases, and popular in Redis. CRDT support in enterprise and Couchbase mobile sync systems. Sync strategies. Pull-based sync. Client periodically asks, do you have updates? Simple but wasteful. Push-based sync. Server pushes updates via WebSockets, push notifications, more real-time, and hybrid, which is the best practice. Pull on app start, push for live updates, background retry for failures. Designing sync layer in mobile application. Architectural components, local database, sync manager, conflict resolver, network service, retry queue. Important rules. Never block UI for sync. Always persist pending operations. Retry with exponential backoff. Log sync failures. Fintech level design. For point of sale system transaction flow, you will save the transaction locally and mark as pending sync. Process payment. Send it to server. If success, mark synced. If failed, retry queue. Conflict rule. Server validates double spending. Terminal reconciles later. This prevents fraud and inconsistency. Common mistakes: relying on timestamps only, no retry mechanism, no audit logs, no version control, blocking UI until server confirms. The architect mindset when designing sync: ask, what happens if network disappears for 24 hours? What if user has 3 devices? What if 2 devices update the same record? What if server partially fails? Can we replay events safely? Synchronization is not about API calls, it's about distributed system thinking. At small scale, sync seems easy, but at scale it becomes one of the hardest problems in system design. Thanks for watching and see you next video.